Being a meter technician can be an interesting job because there's a natural variety in the types of situations that you'll have to deal with each day. At one location, you may be replacing a single-phase residential meter on a private home. Your next location may require you to work in an enclosed meter room in an apartment building, or on a transformer-rated meter installation at a local industry. The important thing is that regardless of its location or purpose, each job must be done safely. In this program, we're going to take a look at some of the things that you have to take into consideration every day when doing meter work, whether you're in the field or back at the shop. When we begin, we'll introduce some basic safety guidelines that can be applied in almost any kind of job. Then we'll take a look at two types of safety hazards that are common to most meter work. They are physical hazards and electrical hazards. Then we'll follow along as several typical metering jobs are performed so that we can see how the meter technician uses his company's guidelines to deal with the safety concerns at each location. As you watch this program, keep in mind that while the situations and procedures shown are typical, they're only meant as examples. The actual situations that you'll encounter and the safety guidelines that you'll be expected to use may be different depending on your company's procedures and equipment. Please be sure that you're thoroughly familiar with the equipment and safety procedures that you'll need to use before beginning each job. Unlike many other jobs, a meter technician may have to work alone at a dozen or more different locations in a day. The meter installation at each location can be totally different, with a different set of problems and hazards from the one before it. This means that you must use your knowledge, awareness, and common sense to analyze a wide variety of situations so that the work can be performed safely. Keeping this in mind, there are three basic guidelines that can be used in almost any situation to make sure that a job is done as safely as possible. They are: know the requirements for the job, plan the job carefully, and follow through by using the proper work methods. The first guideline is to know the requirements for doing the job right. There are many types of meter installations on a system, and you must rely on your knowledge and experience to analyze the requirements of each situation. You must be able to look at a meter installation and identify the equipment, how it's hooked up, and any hazards that are present. Attempting to do a job that you're not familiar with may result in an accident. If you're not certain what to do, ask your supervisor. If you guess, and guess wrong, it may result in an accident that can damage equipment, cause a personal injury, or worse. Once you know what to do, then you can do the job safely. Planning the job carefully is the second guideline. When you get to the job site, take a few minutes to make a visual inspection of the meter installation. Make sure that you're familiar with the equipment and how it's installed before you begin working. This is the perfect opportunity to mentally run through the steps that you'll be using to do the job. If you find any unsafe conditions or unfamiliar procedures, call your supervisor. Knowing what to do and planning the job carefully are not enough, however. You must follow through with the third guideline, using the proper work methods to do the job. This means to always follow all appropriate company procedures and use only the proper tools and equipment. Making do or taking shortcuts is never a good idea. Always make sure that you use the proper protective equipment, such as a hard hat, eye protection, and rubber gloves where required. If you're not sure whether you should wear a piece of safety equipment or not, wear it. It's always better to be too safe than not safe enough. Keep in mind, however, that no safety equipment or guideline can offer you reliable protection unless you're aware of the hazards around you and you're alert to the consequences of those hazards. The attitude that you bring to the job can make a big difference in your ability to remain alert. Working around potentially energized electrical equipment, even if it's supposed to be dead and grounded, is serious business. You have to keep your mind on what you're doing. Bringing your personal problems to work or letting your mind wander can lead to disaster. Remember, you can't tell by just looking whether something is energized or not. And with electricity, you won't get a second chance. Well, we've taken a look at some of the guidelines that can make your meter work safer. Review the material in your text on this part of the program and answer the questions. When we come back, we'll begin our look at typical job hazards common to meter work by identifying some of the common physical job hazards. A big part of working safely is identifying where the job hazards are. For instance, the most common meter technician accidents generally involve physical hazards, like those found in material handling or conditions at the job site. In this part of the program, we're going to identify some physical hazards that often cause problems. However, keep in mind that we can't list all physical hazards or rank them according to the possibility that they might occur. There are just too many possibilities. Each system is different, and each installation on that system can also be different. So you'll have to rely on your experience and remain alert for hazards as they develop. Well, let's begin with material handling. There are three main guidelines here. They are using the proper safety equipment, using the proper lifting techniques, and maintaining good housekeeping. The safety equipment used for material handling often varies with the job. In warehouse situations where material and equipment can be stacked up or put on shelves, a hard hat and foot protection are usually required in almost all cases. Some materials that are commonly handled, like glass meter covers or lengths of wire, can cause cuts, abrasions, and puncture wounds. It makes good sense to wear leather work gloves and proper eye protection when handling materials like these. Other substances, like cleaning fluids, can be toxic or corrosive. They should only be used in well-ventilated areas and with the proper protective gear. The second area of concern in material handling is lifting loads, like a box of meters. Using the proper lifting techniques will help you avoid muscle strains and back injuries. First, make sure that the size and weight of the load can be managed by one person. If you have any doubt about being able to manage the load, get help. Before you begin to lift a load, make sure that you have good solid footing and that your weight is balanced on both legs. Bend your knees so that you can reach the load. Get a good grip on the load, keeping your back straight. Never bend over to lift a load. This can result in a terrific sideways strain on the spine that can cause permanent injury. Lift straight up, using the muscles in your arms and legs. Avoid sudden or jerky movements. Hold and carry the load at waist level, keeping the weight balanced. At the truck, lower the load by bending your knees and keeping your back straight. All materials should be properly stored on trucks and in all other work areas. So these boxes of meters will have to be moved into position and secured. Be careful when shifting the load into its stored position to avoid overextending your reach. Overextending tends to throw you off balance and to put extra stress on muscles. Storing materials is an example of the third area of concern in material handling: good housekeeping. Whether you're working in the shop or in the field, keeping equipment and work areas neat and orderly will make your job easier and safer. It allows you to keep track of the materials at hand and will eliminate hazards caused by loose shifting objects and unnecessary clutter. Trash and other debris should be disposed of properly. Like material handling, the physical conditions found at each meter installation can also affect your safety on the job. Most meter installations are located on private property, where the customer is responsible for the maintenance of the area. So whenever you go onto a job site, you must be especially alert for existing conditions that could affect your safety. Observe and follow any warning sign on the premises. If there is a no trespassing sign, don't enter the property until you notify the owner or manager and get permission. If the sign indicates the need for protective equipment, such as eye protection or a respirator, always follow its directions. If a warning sign indicates that guard dogs are on the premises, contact the owner from the outside to make sure that it is safe before entering. When meter installations are located some distance from the building entrance, it's a good idea to form a mental picture of the route taken in case you need to make an emergency exit. Care should be taken when going up or down stairs. Always use the handrails and be alert for any foreign objects and broken or loose treads. The metering area should be clean and accessible, with enough light to allow normal work on the meters. There should also be sufficient clearance between the meter installation and any obstructions in all directions. If a meter installation has become inaccessible or hazardous because of storage, redesign, or any other reason, do not attempt to enter the area. Any abnormal condition should be reported to your supervisor so that the customer can be contacted to correct the problem. Don't attempt to correct the problem yourself unless there is an emergency. If the meter equipment is located in an enclosed space, such as a vault, there should be provisions for ventilation. If not, the air inside must be tested for its oxygen level and for explosive gases by a qualified person using suitable test equipment. If the air checks out as being safe, the space may still have to be force ventilated or the air monitored for the duration of the job depending on company policy. If the meter is located at a private home, it is probably located on the outside of the house. However, all of the requirements to check for physical hazards remain the same. If possible, notify the customer that you're on the premises and that you need to work on the meter. A customer's home is private property and must be treated with care and respect. The area around the meter should be free and clear of obstructions, such as overgrown foundation plants and debris. Remember, you'll be working on energized equipment, so you shouldn't have to overextend your reach or work off-balanced. In addition, foundation plants can provide a good electrical path to ground, especially if they're wet. Plants can also harbor stinging insects and other pests. If the area is too overgrown, it is best to report the condition to the customer so that it can be corrected. Finally, you should check the ground around the meter installation to make sure that it will provide good footing while you do the job. Well, in this part of the program, we've taken a look at some of the physical job hazards that are common to meter work. When we come back, we'll take a look at another common type of hazard encountered by meter technicians every day: energized equipment. Until then, read over the physical hazards section of your textbook and answer the questions. So far, we've been looking at various physical hazards that you may come across in meter work. Accidents occurring due to these hazards are more common than those caused by electrical hazards. There seem to be a couple of reasons for this. The first is that there are more opportunities for non-electrical accidents to happen. The second is that working around electricity creates a sense of respect and natural caution. You can't see electricity, so you can't tell by looking at it whether equipment is energized or not. And electricity can shock, burn, or kill a victim easily. This is true of the secondary circuits found in most meter installations as well as primary circuits. For instance, if you're working on a meter installation and a fault to ground occurs, the current flow can suddenly jump up to the limit allowed by the fusing on the distribution transformer. So it's always best to be cautious when dealing with electricity. In this part of the program, we're going to take a look at the effects of electricity on the human body. Then we'll describe the use and testing of some of the safety gear normally used around electrical hazards. The electrical dangers to the human body basically result from current flow or from electrically generated heat. The effects of current flow can be a stun, where there is a temporary loss of muscle control, a cardiac arrest, where the heart stops beating, or a deep electrical burning of tissue or muscle. The danger from heat is the other type of electrical hazard. An electrical flash or fire can result in excessive heat that can lead to serious surface burns on the body. We'll talk more about flash burns in a few minutes. First, let's take a look at why current is harmful and at some of its possible effects on the human body. Current flow is dangerous because the human body is a natural conductor of electricity. Current always takes the path of least resistance to ground, and that path may be through a person's body. We can use this illustration of a human body to see how current flow affects the functions of muscles and body tissue. If the left foot is grounded and the left hand touches an energized conductor, the shortest path to ground is through the left side of the body. Current taking this path affects only the one side and, depending on the actual path, may or may not have an effect on the heart. However, if one hand contacts an energized conductor while the other contacts another conductor or a ground, current can flow from hand to hand, across the chest, and directly through the heart. The chance of severe damage is greatest when the current flow is directly through the heart. How severe the damage is depends on the amount and duration of the current flow. A stun is the least severe. It is the result of between 1 and 50 milliamps, less than 1/20th of an amp. During a stun, there is a sensation of shock and some loss of muscle control. Above 50 milliamps, there may be a cardiac arrest or fibrillation if the current passes through the heart. This is where the individual heart cells lose their natural rhythm and the heart stops its pumping action. Fibrillation can result in death without swift medical attention. The most severe electrical burns result from current flow in excess of 200 milliamps. This is still only 1/5 of 1 amp. Regardless of where the contact is made on the body, this level of current flow can cause deep electrical burns, chest muscle contractions, and heart stoppage for the duration of the shock. The severity of the effects of current flow and its path through the body depend on the resistance encountered. The body's resistance to current flow is different in different areas of the body. For example, muscle tissue offers much less resistance to current flow than dry skin. So current is less likely to flow across the surface of the skin and more likely to flow through the muscle. This is why electrical burns are often so severe. Now, the last type of electrical hazard that I mentioned was a flash burn. A flash burn is an injury from the heat and ultraviolet light associated with an electrical arc or flash. This type of arcing can happen if a meter is pulled when under load. Then the meter acts as a switch, breaking the load. The resulting arc can ionize the air behind the meter, causing an electrical flash. The heat and ultraviolet light from the flash can burn the eyes and any unprotected skin with disastrous results. Whenever there is a danger of an electrical hazard, whether it's from current flow or flash burns, it's a good idea to wear the proper protective equipment. This includes eye protection, like these safety glasses, or the full face shield attached to this hard hat, and long-sleeve cotton work shirts or jackets. Cotton shirts protect better during an electrical flash because the material is slower to burn and may not even ignite during the flash. When cotton does burn, the material falls away from the victim. Material with a high artificial fiber content, like polyester, tends to melt and cling to the victim, prolonging the burn and making it worse. Rubber protective gear, like these rubber gloves, is commonly used to provide insulation from current flow and should be worn whenever there is a possibility of coming into contact with energized equipment. Now, you may have been issued 2 pairs of rubber gloves. The first pair, like these, are Class 0 rubber gloves. They have a maximum voltage rating of 5,000 volts. This other pair of gloves is Class 2 rubber gloves. They're rated for 20,000 volts. Rubber gloves are made by dipping forms in liquid organic rubber until the correct thickness for the rated voltage is obtained. Like other organic substances, the rubber can be damaged or decompose under some conditions. So all rubber gear must be tested and certified for use periodically. After it has been certified, it is stamped with a date that indicates the day that it should be turned in to be tested again. Make sure that any rubber gear you use has a valid date. Because rubber gloves are important to your safety, it's a good idea to field inspect your gloves regularly as well. First, remove the leather glove cover from one glove and carefully inspect the surface of the rubber for damage. Pay special attention to the area between the fingers and the palm of the glove. These are areas that normally receive the most wear. If there is no apparent damage, hold the cuff of the glove together and flip the glove over to trap the air inside. Visually inspect the glove again. Then hold the inflated glove next to your face and one ear and squeeze. This way, any air escaping from tiny pinholes or cuts can be detected more easily. When you're finished with the glove, inspect the leather glove cover for signs of cuts, tears, or loose stitching. Any weak spots in the glove cover could allow the rubber glove to become damaged. Then replace the glove cover on the glove and proceed to check the other glove and cover. Rubber gloves should never be used without their leather glove covers. Well, in this part of the program, we've defined two electrical hazards, current burns and flash burns, commonly found on the job, and described their effects on the human body. Then we identified some of the protective gear, like proper clothing, eye protection, and rubber gloves, used by meter technicians to protect themselves from these electrical hazards. Take some time now to go over the material on electrical hazards in your textbook to make sure that you're familiar with the content, then answer the questions. When we come back, we'll begin applying some of the information that we've covered so far in the program to actual jobs in the field. Up to this point in the program, we've looked at different kinds of problems or hazards common in meter work. Now we're going to follow along as an employee uses his knowledge of safety in meter work to perform two typical jobs. First, in this part of the program, we'll see a single-phase 320-amp meter with a broken glass cover replaced. Then we'll watch as a three-phase 480-volt meter is installed at a new location. Keep in mind that while these jobs, as well as the equipment and procedures used, are typical of many kinds of meter work, they are only meant as examples. Your company's procedures, guidelines, and equipment may be somewhat different. Make sure that you know how your company expects these jobs to be done. A call has been received reporting that the glass cover on this single-phase 320-amp meter has been broken. As the meter technician approaches the meter, he visually checks the meter and the area to determine the extent of the problem and to make sure that there are no obvious physical hazards. Since he has no further information as to the damage to the meter, the technician is already wearing a hard hat with a face shield and his rubber gloves. If the meter is causing an obvious hazard, he is already prepared to take immediate action. He makes a careful visual examination of the meter to see if the load is still being carried and if there are any burn marks or other signs of overloading. The meter disc is not turning. The meter may be damaged, jammed with broken glass, or there may be no load on the circuits in the house. However, since no one is home, the meter technician has no way to determine if there is a load on the circuit or not. So the meter will have to be bypassed or disconnected before it can be replaced safely. Since the meter socket and box appear to be in good condition, he will bypass the meter. The technician removes the cover compartment so that he can reach the terminations where the two 120-volt legs of the service are connected to the base of the meter socket. each leg has a line and a load termination. The fifth termination is from the system neutral. He makes a quick visual inspection of the compartment and the socket to make sure that there are no obvious hazards. The voltage is tested between each of the 4 energized terminations and the ground. The reading is approximately 120 volts phase to ground on each termination. Then he checks to make sure that the voltage line to line and load to load is 240 volts. Finally, he checks the voltage from the line termination to the load termination on each leg to make sure that there is no potential difference. A burned out meter element or a bad connection could cause a voltage difference between the 2 terminations. Since the reading was 0 on each leg, he knows that it is safe to connect the bypass link on each leg of the circuit. If there had been a voltage difference between the line and load side of the same leg, connecting the bypass link could have caused arcing. He loosens the bypass stud nuts on each leg. The nuts are used to hold the bypass link in place. Then he installs a bypass link on each set of studs and tightens the nuts to make sure that the bypass link stays in place while he works on the meter. The meter socket and meter are now bypassed, but still energized. Now the meter can be removed without creating a load break situation. The technician removes the retaining ring so he can get at the meter. Since the meter is still energized, he must wear his rubber gloves to protect himself from accidentally grounding the meter as he works. He cleans away the broken shards of glass and gives the meter a quick visual check to make sure that it is still structurally sound. If there are loose or damaged parts, they could come apart as the meter is pulled from the socket, creating a short circuit. The meter looks good, so he pulls it out of the socket. Once the socket is clear, he visually inspects it for any signs of overheating, loose connections, or damage that would require it to be replaced. Next, he makes a voltage check from each of the 4 jaws in the socket to the neutral. He gets 120 volts in each case. Then, he checks from line to line and load to load to make sure that he still gets 240 volts. Finally, he checks from each line to its load to verify that those readings are still 0. The technician is satisfied that the meter socket is in good condition and that the voltage readings indicate that there is no damage internally, so he can go ahead and install the new meter. He checks the back of the new meter to make sure that there are no obvious problems that could cause a problem after the meter is installed. He lines up the blades on the back of the meter with the jaws on the socket. Then he firmly pushes the meter into the socket and checks to make sure that the meter is fully seated. All that remains is to install the retaining ring, remove the bypass links, tighten the nuts down on the studs, replace the cover, and seal the meter box. When the job is finished, the technician visually checks over his rubber gloves just to make sure that they weren't damaged by the broken glass from the meter. Well, in this part of the program, we watched as a meter technician replaced a single-phase 320 amp meter. The technician was careful to wear the proper safety gear and to check at each step of the job for physical and electrical hazards. Now, turn off the tape and take some time to review this material in your text, and when you're ready, answer the questions. When we return, we'll see a new 3-phase meter installation. Well, in the last part of the program, we watched as a meter technician changed out a 320 amp single-phase meter that had a broken glass cover. Now we'll continue on as the technician makes a new 3-phase meter installation at this building. Remember, these jobs are meant as examples to illustrate the safety issues involved. Your company may have different requirements to do a similar job. Make sure that you're aware of the procedures and equipment that you'll be expected to use. Well, as I said, the meter technician has a work order to install a 3-phase self-contained meter on this building. Since the conductors into the meter box and the meter socket may be energized already, He puts on his safety gear before opening the meter box. When he's ready, he removes the cover of the meter box and makes a visual inspection. The base of the meter socket has 3 pairs of terminations connected to it, a line and load conductor for each phase. There is a neutral connection on the side of the cabinet as well. When he checks the voltage on each termination to the neutral, he finds normal voltage on each of the line terminations and no voltage on the load terminations. So the line side of the socket is energized and the load side is not. To make sure that there is no possibility of a load connected to the circuit in the building, he opens the main panel disconnect switch in the building, isolating the building from the meter. Back at the meter cabinet, he takes off the cover used to protect the empty socket and makes a quick visual inspection for socket jumpers or bypass links. Using his voltage tester, he checks each line side jaw to neutral and finds normal phase to ground voltage. A check of the load side jaws to the neutral shows 0 voltage on each phase. Checking each line jaw to its load jaw also indicates 0 voltage. Then he checks the phase-to-phase voltage between each of the line side jaws to make sure that he gets a normal phase-to-phase reading. When he tests the load side jaws phase-to-phase, the reading is 0. If the reading showed a voltage, an internal socket problem would be indicated. Now that he is confident that the meter socket and the terminations are in good order, he can install the meter. He begins by loosening the bridging nuts on each termination. Bridging nuts are used on this type of meter to provide a way to isolate the meter socket from the termination. If the nut is loosened, there is an insulated gap between each termination and its connection to the base of the socket, and the meter socket is isolated from that termination. If the nut is tightened, a connection is made between that termination and the meter socket, forming a circuit. Once all of the bridging nuts are loosened, the meter socket is isolated from all of the line and load terminations. The technician checks each jaw phase to neutral and phase to phase to verify that the reading is 0 in each case. The technician takes this opportunity to make a careful check of the connections inside the socket before plugging in the meter. All checks on the equipment so far have been positive. The socket has been isolated from any load or power source in the building by the disconnect switch. The socket has also been isolated from the terminations to each phase by the bridging nuts. So the meter technician knows that it is safe to go ahead and plug the meter into the socket and to install the retaining ring. Now all that remains is to close the meter into the circuit and the installation will be complete. He begins by checking the voltage across the bridging nut on the line side of A phase. He gets a fraction of the normal voltage. This is expected because the voltage is being split between the voltage tester and the phase's high impedance potential coil in the meter. So he knows that it's safe to close the bridging nut between the line termination and the socket base. When he checks the voltage between the line side and the load side of the phase on the socket base to neutral, he now has normal phase to ground voltage. Just to make sure that there are no shorts involving phase A inside the socket base, he checks the line and load terminations of B and C on the socket base to neutral. They read 0. Finally, he checks across the load side bridging nut on A phase to make sure that the connections up to this point have not created a short in it. The reading is still 0 volts, so he knows that it is safe to close the load side bridging nut. With the first phase checked and properly connected through the meter, he will continue the process with the other 2 phases. Once all 3 phases have been connected, he'll make one last visual inspection of the cabinet to make sure that everything is in order, and close the cabinet. Finally, the technician can report that the meter installation is complete, and the customer can close in the disconnect switch energizing the building circuits. Well, we began this program by listing 3 general safety guidelines that apply in almost any kind of work. They are: know the requirements to do each job right, plan each job carefully, and follow through by using the proper work methods. Then we identified some of the physical and electrical hazards commonly found in metering work. Finally, we have watched as a meter technician changed out a broken single-phase meter at an existing installation and then installed a self-contained three-phase meter on a new installation. We saw that he checked for hazards at each step of both jobs and took precautions to make sure that each job could be completed safely. Remember, it's important for you to use your knowledge of your system, stay alert, and use your common sense in every job that you do. Working safely is your responsibility. Your life may depend on it.